So let's get started. This is 3.3, the first derivative test. Derivative test. So things we've talked about. The first derivative test is related to finding out information about the increases and decreases of a graph. The first derivative test it tells us information, tells us when the graph is increasing. Let me do this in a different color. Increasing or decreasing. I should say when the graph of f of x. The first derivative test helps us to figure out if the graph is increasing or decreasing. Very similar, very related to our extreme value theorem, right? The extreme value theorem, you found critical values where the derivative was equal to 0 or dne, right? You found those critical values, and then you plugged them into f, to find max and min, right? To find max or min. Plug them into f, right? So that was the extreme value theorem what we did before, right? We found our critical values where the derivative was 0 or dne, and then we plugged those critical values into our main function to find those maxes and mins. Yeah? That's what we did with that extreme value theorem. We found the critical values, plugged them in. In the first derivative test, you're doing something similar. First derivative test. You are still finding the critical values. You're still finding the critical values, right? It's still important to know where the maxes and mins are, where the zeros and dne's are. But instead of plugging into the f equation, you're going to use these critical values to determine ranges, sections of the graph. And you're going to plug those sections into f prime. Use the critical values to create intervals, chop up the graph, and then plug in to f prime to see if it's either positive or negative. Positive is increasing. Negative means the graph is decreasing. So with the first derivative test, you're plugging into the derivative function. You're plugging into f prime. You're determining f prime. is positive or negative. Right? First derivative test, you plug into the first derivative. In the extreme value theorem test, you're plugging into the original equation to determine the value in the original equation. Here, you're not plugging in the critical values, you're plugging in the section of the interval. I'll talk more about this. I'll show you an example in a second. But you're finding the critical values, you're chopping the graph into chunks, into like sections where before this critical value, let's find out what's happening over here. Between this critical value and this critical value, what is the graph doing over here? You're determining, and you're plugging into the derivative equation to determine in that section, is the graph increasing or is the graph decreasing? In the section between these two critical values, is the graph increasing or is the graph decreasing? You're plugging into the derivative, f prime. It's the first derivative test. It's not the no derivative test, right? I'm imagining a SpongeBob meme. It's the first derivative test. Yes, it's the first derivative test. You're plugging in the derivative. Plug in the derivative to determine positive, increasing, or negative, decreasing, right? So that's the first derivative test. You make these intervals, these chunks of graph, and then you see what is this chunk doing? What is this chunk doing? Is this chunk going up? Is this chunk going down? And the critical values are your your sort of edges of these chunks, the edges of these intervals. So let me give you an example. And a graph like this here. Here's f of x. In the first derivative test, what we do is we find the critical values. Here and here are critical values. Critical value where the derivative equals 0. Critical value where the derivative equals 0. Right? So that is like a section here where let's say x is like, let's say this is -2. Let's say this is -2, and this is 1. Yeah, so this is not, okay, let me clarify. This is not we're not taking a test. We're not taking a test. This is not like our first derivative. This is not like it's just called the first derivative test. It's like these are notes on a topic. The topic is called the first derivative test. This is not, we're not taking notes about a test that we're going to take. I mean, you are going to take a test about this. This is important to know. But this is not like, it's not notes about a test. It's notes about a topic. Chapter 3.3, section 3.3, the topic is called the first derivative test. Just like we have the extreme value theorem is a thing in calculus, the first derivative test is a thing in calculus. It is a topic, a way we use derivatives to determine information in calculus. This is not notes about a test that we're going to take about our first derivative test. No, it's a topic called the first derivative test. I'm showing you how to do the first derivative test. Just like we did the extreme value theorem, we're going to do the first derivative test. We're going to talk about this topic. I know, it's a little, call it, whoops, shoot, I will never know. Well, no, I know why. It's because you're testing the graph. You're testing the graph is what you're doing. You're testing the graph. Anyway, here's -2, and there's a +1, and we have these critical values. I could zoomed in more when I did that. Oh well. So here's a graph. What I want to determine is, where is the graph increasing and decreasing, right? So let me show you what I mean. In this section of graph, right, from negative infinity until x equals -2, right? In this section of graph, right? So here's like a barrier. This line here is telling me that this is like an edge of a section of graph. Something is happening in this first section of graph, and it changes at this 0 point. In this section, if you look at this part of the curve here, the graph is going to be going down in this entire section of graph, right? From -2 backwards, the graph is it's doing one of two things. It's either only going to increase or only going to decrease. Here we see it's only decreasing. These critical values tell us the locations where there is a change in the like increasing or decreasing shape of the graph. These critical values tell us where the changes happen between decreasing sections of the graph and increasing sections of the graph. Right? From here to here, where x equals 1, in this section, right, the graph was decreasing here, and then it changed at this critical value. These are why they're critical values, because they're places where the graph changes. Changes from decreasing, and now the graph is increasing. The function is growing from here to here. It grows at different rates, but it's continuously increasing until this x equals 1. And then from x equals 1 and on to positive infinity, the graph is decreasing again. So here I have decreasing, a decreasing graph. F prime is going to be less than 0 in that section. In the section here, the graph is going down, my graph is decreasing, and so my derivative is going to be negative. My derivative is negative in this entire section. No matter which point I pick in here, every point I plug in, if I plug in a -3, -4, -5, -10, it doesn't matter. Every single value of my derivative graph will be negative in this section because this is where it's decreasing. At x equals 2 in this spot, the derivative is 0, right? You see here f prime is 0. Right at -2. The derivative is 0 right there. And then after that, here it's increasing. Right, my graph is going up. F prime is greater than 0, or positive. Increasing, increasing, increasing the entire time from -2 until positive 1. My graph increases. And in the first derivative, my first derivative test, the test is if I plug a number into my derivative somewhere between -2 and 1, right? Like if I plug a 0, or if I plug a -1, those values will all be positive values. And they're only going to be positive between these two sections. There will never be a derivative that is negative in this chunk, because the only places where it changes from positive to negative, or potential changes, are at these critical values. These critical values are where the derivative changes from positive to negative or negative to positive. The only places these happen is the critical values. That's why they are so critical. And then again, at 1, my derivative was positive. Now I'm going to go back to being negative, decreasing again. F prime is less than 0 or negative again, because my graph is now back to going down. my graph is decreasing. F prime is decreasing there and there. F prime is increasing in that section over there. So F prime is negative in this section, negative in this section, and positive in this section. And that's the first derivative test. This idea that you are determining the increasing or decreasing sections of a graph by plugging into the first derivative. Is it increasing in this section? Decreasing in this section? What's happening? You're testing it by plugging in a value somewhere in this range into your derivative. And if it's negative, then you know that in that section, the graph is strictly decreasing. It is never going to increase in this section because the only time it can change is at these critical values. The only time the derivative changes from positive or negative, changes signs, is at these critical values. The only time the derivative can change signs. So that idea, that is the first derivative test, right? If the derivative is positive, then it's increasing for that section of the graph. The only place it changes is these critical values. We find these critical values to find the intervals, right? So again, we use the critical values to create the intervals, and then we plug into f prime to see if it's a positive, where your graph is increasing on the interval, or decreasing, negative, where it's decreasing on that interval. So you find the critical values, use the critical values to make like sections of your graph. Very similar to what we did for the extreme value theorem, right? In the extreme value theorem, you found these points. You made your chart, right, with these points, and you determined by plugging into f, you determined which was the highest point, which was the lowest point, right? Because those are the only spots, right? Those critical values are the only spots where it reaches a max or a min potentially. Because of those critical spots, everything in between those critical values is doing one of two things. It's either increasing, graph's going up in that section between the critical values, or it's decreasing between the critical values. So the first derivative test, you're plugging into the derivative. You're testing the derivative to determine in the section, is it increasing or decreasing? Questions about this? Questions about this? Confusion, questions, worries? Okay. What time are we out of here? 25. Okay, good. I got 25 minutes. 20 minutes. Great. All right. So let me show you. There are 4 potential ways that critical values can change this. Change these graphs. So let me summarize here. Do this in red. The only place where f prime can change from increasing to decreasing is at a critical value. The only place where the derivative can change, where the function can change, I should say, where the function can change from increasing to decreasing is at a critical value. Increasing. The only place where the derivative can change from increasing to decreasing is at a critical value. And there are sort of like 4 potential situations that these critical values can be in. Well, maybe a lot more than 4. Let me give you some examples. Let's see. How do I say? Kinds of changes. Kinds of changes that can happen. Here's the 4 kinds of changes that can happen. So the only place is at these critical values. There's 4 different kind of ways these critical values can occur. Right? 1, if you go from decreasing, and then you land on a critical value here, to increasing. You go from decreasing to increasing. Here f prime equals 0. You go from negative to positive. F prime changes from negative to positive. Right? So that situation, if you have this transition between your critical values, at this critical value you have this edge here at some value, and before that value you have a negative derivative, after that you have a positive derivative. F prime changes from negative to positive. If that's the case, this means you have a local minimum. You have a minimum, right? Think about it. If you go from negative, you bottom out to being positive, if you were decreasing and then you were increasing, you hit some bottom. Right? So that is a little relative minimum or local minimum of a graph, right? If you change from negative to positive. So if f prime changes in that way, you know you get a bottom there, right? That's a minimum. You don't even need to tell if it's right? If you plug in f in this graph, if you plug f in for the critical value, you'll get some number. But the derivative test tells you if it's a minimum or maximum number, which direction you're going. So that's 1. Another potential change is the other way. If f prime is positive, and then you hit your critical value, and then f prime becomes negative. Right? So if f is increasing, positive, here f prime is 0 on this interval, and then you have f prime is negative here. Let's say here f prime is positive, and here f prime is negative. Here f prime is negative. Here f prime. Let me make this a little bit better. Hold on. Let me clarify this. Hold on. F prime is negative. Here, f prime is positive. I don't care what number. I just care about negative, positive, negative is all I care about. here f prime is negative on this side, f prime is positive on this side. So if f prime changes from positive to negative, that is a local maximum. So that's another way to determine the shape of a graph. Now you see how it's changing. The derivative was negative, and then it was 0, and then it was positive. It was a negative derivative, graph going down, and then the derivative was 0, and then the derivative is positive. Here, if f prime is positive numbers like positive 5, positive 4, positive 3, positive 2, positive 1, and then it hits a 0, and f prime is a positive number, positive 5, positive 4, positive 3, still positive, less positive, but still positive, positive 2, positive 1, now f prime is 0. It was positive f's, and then it became a 0, and now it's negative 1, negative 2, negative 3, negative 4. F became negative. You changed from positive to negative. You were a maximum. That's going over a hill, right? Here, f prime is negative 5, negative 4, negative 3, negative 2, negative 1, 0, and then positive 1, 2, 3, 4, 5 as it goes up. So f was negative, and then 0, and then positive. So those are some changes that can happen, going from negative to positive, positive to negative. Sometimes there are other kinds of changes. You have a situation where a graph might do something like this. Here is a critical value. This is where the derivative is 0. It flattens out, right? The graph flattens out. But the derivative, f prime, was positive here, and after it, it's still positive. F prime is still positive over here. F prime, still positive. So if f prime does not change, if f prime does not change signs, it is not a max or min. It's neither one. And of course we can do the same thing going the other direction, right? We can say decreasing, flatten out, decreasing there. And again here, f prime is 0, and it did not change signs, right? Here and here, f prime was negative here, and f prime is negative here. Oops, no, not 1. Negative. F prime is positive here. F prime is negative. So if f prime does not flip signs from section to section, you know it's not a max, it's not a min, it doesn't go any direction. It's this little s. It makes a little s. Okay. So these are some situations where you have the 4 situations where your derivative is equal to 0. Your derivative is 0, and you have these critical values, these sections of the graph where you're testing the first derivative. It's the first derivative test. You test the first derivative and you see what is the first derivative doing. How is this first derivative changing? Is it changing from positive to negative, negative to positive? Is my graph curving up and then down? Like what shape does the graph have? That's what this first derivative test tells us the shape of the graph. First derivative test tells us the shape of the graph. The first derivative test tells us about the shape of the graph, about the shape of the graph. Increasing, decreasing, curving up, curving down. Various kinds of changes that happen with our derivative test. Okay. You're plugging into the first derivative. You test your derivative. You're finding the critical values, and you're using those as boundaries of your sections. You chunk out the graph, and you'll see what's happening in this chunk. It's only going to be strictly increasing or decreasing. It's never going to change. The only places it changes is on those critical values. The only place where the derivative changes, potentially changes sign. Sometimes it doesn't. Sometimes you get something like this. But the only place that it can change is at the critical values, where we're changing from positive to negative. Those are the only spots, right? Look at this graph here. The only spots that the graph can change from decreasing to increasing is at these critical values on the edge here. And so we use the first derivative test to test, well, what's happening in this interval? In this interval, is the graph going up or down? So the first derivative test is we find the critical values. We use those critical values to create the intervals. And then you plug in a number in that interval. You plug some value in the interval in the derivative to see if that section is increasing or decreasing. The only place where the derivative can change from increase to decrease is at a critical value. Okay? If it changes from decreasing to increasing, just use your hand, imagine decreasing to increasing, then you have a minimum. If the graph changes where the derivative is positive and then the derivative becomes negative, the derivative is positive and then negative, that's going to be a maximum. Derivative positive, derivative negative. That's going to be that point, that critical value, that derivative equals 0, that critical value is going to be a maximum value. If the derivative is negative and then becomes positive, that's going to make that critical value is a minimum value. So you can see the shape of the graph. Oh, it's going to curve this way and it's going to curve up like that. If it goes from positive to positive, you know you have the little S shape. The graph's got an S here. Positive to positive. Or negative to negative. Graph's got a little S going down. S going down. So this is the first derivative test. You test your derivative to see the shape of the graph, what's happening in the sections. So we're going to do some practice tomorrow using this first derivative test. We're going to determine some of the shapes of these graphs and figure out how to use this test to determine maxes and mins and all these different kinds of things. So we have two tests that we've done so far. We have this extreme value theorem where we find the critical values, plug into the f equation, the original function. The extreme value theorem shows us these maxes and mins, right? The absolute max and mins. And in the first derivative test, you plug into the derivative, you find those critical values, plug into the, make these intervals, and then plug in the sections before and after the critical values to determine what's happening with the graph, what the shape of this graph is doing. Is it decreasing? Is it increasing? What's happening here? So you find those sections and you determine the shape of the graph. So we'll go over this more on Tuesday. Questions about this before we go? Mr. Mitchell, what does that squiggle mean? Mr. Mitchell, why is that symbol? Mr. Mitchell, what about this other situation? Yeah, I'm going to post this to Schoology for sure. So this is just the beginning of the end, everyone. Using the derivative to determine these shapes of the graph. Like I said, we'll go over this more on Tuesday. That is it for us today, however. Good job, everybody. Thank you very much. In the chat, type goodbye. Once you type goodbye, you're free to go. I'll post this to Schoology and see you all tomorrow. Bye, everybody.